Hi everyone, my name is Recipe, and today we're talking about how we blew things up in the lab with permission using bomb calorimetry to investigate the resonance energy in benzene. And so we're all familiar with delocalized pi systems or conjugated systems for organic chemistry, where when we do a hydrohalogenation reaction, when we do a hydrohalogenation reaction, we can get some pretty interesting reactivity with this 1,2 kinetic addition, or in this case, this 1,6 thermodynamic addition based on thermodynamic or kinetic control due to the resonance of the intermediate carbocation state, which is shown here by the delocalization of the lack of electron density. It creates resonance energy because of this pi orbital overlap. Um, and that's where we get this interesting reactivity from. But perhaps what's even more interesting is that when we try and do this with something like benzene, we end up getting no reaction. Um, but what's even more interesting is that we can get a substitution reaction which preserves this resonance in benzene when we perform an EAS reaction using Lewis acid catalyst and bromine. And so the reason that we can see this kind of reactivity, but not the addition reactivity, is because of the aromaticity or the stability of the benzene molecule. And so how we define a resonance energy inside of benzene, we're defining it as an energy saver or a stabilizing energy of the molecule. And so usually how we think of this is we have a theoretical heat of hydrogenation, where we take this cyclohexatriene, which is the theoretical or hypothetical model or molecule, compare it with the heat of hydrogenation using a pretty strong catalyst for benzene, and the difference between these heats of hydrogenation is what we're calling the resonance energy. And so our research question comes, what methods can we use to quantify the resonance energy of aromatic conjugated molecules? And if we can quantify the resonance energy of benzene, what can we learn about other conjugated systems? And so the reaction that we're targeting here is this isodesmic reaction. And what an isodesmic reaction means is that we take the number and type of bonds and we make them identical in the products and in the reactants. So we're doing this between benzene and cyclohexane to form C to DT. And so our hypothesis is that where we would usually expect the heat of reaction to be zero for an isodesmic reaction because of the stabilizing resonance energy of benzene, we're going to observe a non-zero enthalpy of reaction. And so we can do that pretty quickly by finding the heat enthalpy formation values for each of these three molecules. And if it's zero, it means there's no resonance energy. But if we obtain a value, we're observing resonance energy. And so when we do this actual experiment, we get a resonance energy of about 31.5, which already proves hypothesis one that there is this resonance energy in benzene. And so just how we obtain these values for references, we basically do a geometry optimization on all of them. But of course, we need to back up our experimental or our theoretical or computational results with some experimentation. And so what we can do here is use bomb calorimetry combined with a Hess's law approach. And so how a bomb calorimeter works is that we load our sample here, put our ignition wire inside, pressurize this with oxygen, stir the water bath around it, and then we can measure the temperature as the sample combusts. And so because we're doing this in the liquid phase and not the gas phase, we have to take into account the enthalpies of vaporization for benzene, cyclohexane, and CDT. And when we apply Hess's law, adding up all of these values, and because these are all balanced, to give our net reaction of benzene plus cyclohexane to give CDT, it's the isodesmic reaction, we end up with the resonance energy of benzene. And so kind of as our check, we're saying that for our second hypothesis, that because we can observe the breaking of aromaticity in the intermediate states of electrophilic aromatic substitution, is expected that the resonance energy of benzene will be a magnitude smaller than the actual energy released during the combustion of the reaction. And so because this experiment is focused mainly on bomb calorimetry, we elected to obtain literature values for the vaporizations. Except for this vaporization of CDT, we were able to use some data previously obtained in fitting it. So that gets rid of these 3 of the 6 steps, makes our life easier. And because benzene is actually a pretty nasty chemical, it says here that's highly flammable, maybe fatal if it's swallowed or enters the airways. That's like really not up to my speed, especially in an undergraduate laboratory, maybe in the research lab. But so this experiment, we experimentally determined the enthalpies of combustion for cyclohexane and CDT. And so how we're actually setting up this experiment is we're plugging this ovular bucket, which we'll add our bomb to. Right now, I'm pressurizing the bomb to 30 atmospheres using pure oxygen. You load that in there, plug in the ignition wires. It doesn't matter which way they go, and then add the water. That's how we had 2 liters of water, and that's how it's calibrated to find the specific heat of the bomb. Turn on the motor, make sure we clamp it down because in the lab, someone had previously used this, kind of blew it up all over the place. And then we add some extra protection as long as our thermocouple, which measures the temperature. And so whenever we measure this temperature, what we get is a plot of the temperature change over time. And there's some interesting, or not, but there's some variables here. So we have the initial time, TI, which is given by 60 seconds after that, which gives the bomb enough time, the calorimeter enough time to equilibrate. The water, TA, is the ignition of the bomb, TC is the maximum temperature, and TF is the final temperature, which is about 90 seconds after max. TB is defined as the time at 60% of the total temperature change, which we're calculating here by taking the difference between the max and the initial temperature, multiplying by 60% or 6.6, and then adding it back onto that initial time. And so because the temperatures are pretty unstable at these red and orange points, or these red and purple points, we do a baseline correction here, which we take the difference between TC and TA and incorporate the slopes of these 2 lines here, R1 being the red region and R2 being the purple region. C and TA are given by temperatures, and A and B and C are given by times. And so we obtain this kind of data for CDT 1, 2, and 3. We run it 3 times. Because we messed up the first run, we didn't let it run long enough. We had to use just the max minus the initial. And basically, we can take this total Q, subtract away the Q of the wire, which is this QUW. That gives us the Q of the sample. And because this is being run at constant volume, we get the change in internal energy, and we can use that using the state function to basically convert it into an enthalpy, which is actually a really small correction factor. Here we have internal energy, the change in the moles of gas, which comes from stoichiometry, the ideal gas constant, and the temperature that exists basically at a middle point in this green region here, where we're actually seeing a temperature change. And then to get in kilojoules per mole, we just divide it by the moles of the sample. And so we end up with our delta H values, which the average is what we use for our final Hess's law approach. You do the same thing with cyclohexene, but the difference is that because we have to load cyclohexene in a capsule whenever we ignite the bomb, we have to subtract away the heat of the capsule, which is known based on a ratio of the energy to the mass. We will say that we forgot to take the mass of the capsule each time, which was a huge mistake, but we would use an average, which probably added a lot of variability to our results. So we do the same thing to determine the delta H values. And before we can actually apply Hess's law using those averages, we were given data to determine the enthalpy of vaporization of CDT using this data here. When we fit it using the natural log of the vapor pressure versus 1/T, we obtain this line, which gives us a slope, and the slope relates to the delta H vapor pressure. Basically, if we take the slope multiplied by R, multiplied by -1, we can get the vapor pressure. And so what that allows us to do is go through and apply Hess's law for this reaction. And so we put in all of our values A through C, which come from NIST, which are literature values. Plug in our combustion, and then our vaporization of CDT, and we get 370 kilojoules per mole. which in accordance with our hypothesis is about a magnitude smaller than the combustion values, which are shown here by the 3,000, 7,000, 4,000 values. Because whenever I calculated the percent difference between our Cygress answer or Cygress result and this result, we saw about a 90% difference. So it shows that maybe bomb calorimetry isn't the best, but it does answer our research question that we can experimentally determine the resonance energy of benzene, maybe perhaps using different models in the future. And so some interesting points of discussion are, is it possible to find the resonance energy of benzene using cyclohexatetraene? And so a couple ways I thought about doing this was by taking these molecules here, making either the product or one of the reactants with this 14-member ring. And actually, we could use Cygress to just calculate these resonance energies already. And we can see that this benzene with prop-1-ene actually gives a pretty similar value, where we're looking at about a 13 kcal per mole difference. And I think that if we actually apply some correction factors, being that this isn't an isotosmic reaction, if we apply some bond enthalpies to make up the difference, we can actually get there. Speaking of bond enthalpies, another question is can we just use bond enthalpies to determine this? And the answer is no, because this model actually determines this model neglects that there's resonance structures here. And so if we basically took the bond enthalpies of formation for all of these compounds and did our enthalpy of reaction, we would end up with 0 because we can't account for the resonance energy in these because we can't account for resonance structures. But I think that if perhaps we could kind of do this half resonated bonds type thing and find a literature value for that, we might be able to apply it. But as far as I know, there aren't any literature values for a double bond in resonance. Some other methods we could use are to compare benzene with this 1,3, basically the non-cyclic version of the molecule. And I actually, again, calculated these things using Cygress, or these formation values using Cygress. And the difference between them is about 17.9 kcals per mole, which interestingly is about half that that we concluded from the isotosmic Cygress results. So be curious to look into more about how we can, close the gap between our Cygress results and our for isotosmic reaction, and comparing these two molecules and how that cyclic nature of benzene attributes to its stability. And finally, we can see that the cyclic nature of this comes into play because we're seeing that these two molecules here, just increasing chain length, have about the same resonance energy. These actually should be located next to each other, whereas this cyclooctatetraene is just a bullet benzene, and benzene's all the way at the top. And the reason is because benzene, as we know, is an aromatic molecule, follows the 4n+2 rule, whereas actually cyclooctatetraene has a 4n rule, which means that it's anti-aromatic. So we're seeing here that the anti-aromatic is actually even more, has a more energy resonance savings per carbon. And I would say it's because these bonds are actually not located here; they're actually located without the ring. Whereas you kind of need to visualize a resonance structure here whenever we take away or add, or whenever we would form a carbocation here. So with that being said, I want to just acknowledge a few people. First being my wonderful lab partner, Vincent, and all of the gummy worms that we consumed while writing lab reports this semester. Also to the teaching assistants, the TAs, Kathryn and James, lab coordinator, Dr. Wagner, and of course the University of Pittsburgh for giving us the opportunity to learn about physical chemistry in the lab space. And so because there's no one in the audience, I'm going to assume that there's no questions. So thanks so much.